Alrighty, good morning, guys. Can you hear me?
Yes.
How are we doing?
Hey, Professor, how you doing?
Good. Are there questions, comments before we get started? Okay, so today's lecture and also the lecture next week are going to be a bit of a mixture. So today, the first part is going to be about multi-period binomial. Multi-period binomial models, and there, what you need to read is Ian Steve Shreve's volume number 1. We are over here in the first chapter. So in particular, this chapter 1.2. But we're also going to start moving into chapter 2. We're going to start looking at, in particular, these conditional expectations down here in chapter 2.3. So what we'll be mainly today is going to be in 1.2. So this is Shreve. This is 1.2, but it's also really over here in the first 3 sections of chapter 2. So 2.1, 2.2, and 2.3. This is what we'll be doing today, but also next time. Today and next time. So that's the first part of the lecture. So this can be a little bit heavy. This is not easy at all. And so I'm gonna in the second part of today's lecture we're gonna do something else. And we're gonna be looking at swaps. And the place to look for swaps is over here in Hull. So the place to look for swaps in Hull is over here in the chapter. So that the place to look for swaps, this is over here in his chapter 7. And we're going to be looking at fixed for floating, interest rate swap. So it is a particular section 7.5 in his chapter 7. So let me write that down. So this here is Hull 7.5. And next time we are going to do basically the same thing, but instead of swaps, we'll be looking at these credit default swaps, or CDS contracts. So they're here in chapter 7.10 and 7.11. So we're going to be doing his chapter 7 for the next couple of weeks, and we're going to be doing multi-period binomial models for the next couple of weeks. I just posted before the lecture today. I just posted homework number 4, and so I wanted to just talk to you a little bit about homework number 4. Let's see if I can find it and share it with you. I have so many open. Homework number 4, where did it go? This one. Alrighty, so I'm hoping you can see my homework number 4 here. So what the big problem in homework number 4 is this problem number 2. And what I put in there was I took some data, and this data here is coming from the swap that we're going to be talking about. And this data here, you're being asked to use and create this bootstrapping method that we talked about last week, So this is being used in this homework. And then you're being asked to create spreadsheets and work with this data here. So this is one of the new things. This is not something that we had in the program, in the course last year. So this is an attempt of making the course more closer to implementation. So to do this problem here properly, we need to know what a swap is. So this is in the second half of today's lecture. And then there's also a question down here, which is a pure math question. So this is related to the first part of the lecture, how to compute conditional expectations of this sort here. So after today's lecture, I was hoping that you guys would be able to do problems of this sort, problem 3, and also this problem up here about taking actual data and writing a little spreadsheet that will allow you to answer some questions about bonds, bond 1 and bond 2 here. Okay. Are there any questions? We had a few more sign on. Are there any questions before we get started? So that's the menu for the next couple of lectures. Okay, so we'll ease into the multi-period binomial model. And the way we're going to do that is I'm going to start with an example. So I'm going to start with an example that is the two-period binomial model. So what we have is we now have 2 coin flips. So we have psi1. I should just write it in general. So we write the example that we're going to do with numbers is a 2-period model, but I could write an n-period model here. So we have psi1, psi2, and so on up to psi n. These are IIDs, coin flips. So what does that mean? Well, psi k can take on 2 values. It can go up to u, and it could go down to d. It comes up to u with probability p. And p is this number between 0 and 1. And you can go down to d with probability 1 minus p, which is again going to be a number between 0 and 1. And the IID, we talked about that last time. So they're all independent of each other, and they all have exactly the same distribution. This p that you have over here does not depend upon k. So the IID Bernoulli's, IID coin flips. And so the way that we built a multiplicative binomial model is by saying, so you have a stock, and at time 0, it's given. So at time 0, you have a constant, and then you define it recursively. You say that Sn, the stock price at time, maybe I should continue to use k here. The stock price at time k is equal to the previous stock price. So Sk minus 1 times the Bernoulli psi k. And so that's the recursive structure. And of course, I can plug in Sk minus 1 has exactly the same form. So here I can write Sk minus 2 times psi k minus 1 times psi k. And I can keep doing this until I get down to S0, psi 1, psi 2, and so forth up to psi k. That's my stock price in the multiplicative n-period binomial model. Of course, I also have a bond, I have a bank, and the bank is given very similar. This is, here we start the bank out at 1. We typically do that just to normalize. And then what we say is that Sk, the price of the bank in the kth period, this is just given as 1 plus r to the power k. So we have ud and r are inputs. So ud and r are inputs. Okay. So we have these two securities we can all trade. And when we trade in these two securities, we create a wealth process. So the wealth is given by, say, xk. The way that wealth is defined is simply just the number of shares that you have times the prices of the various securities, and you add them up. So here we only have two things we can trade. We can only trade the stock, and we can only trade the bond, the bank. Right, so we only have two things that we can trade. So we'll have delta naught shares of the bank. So we'll multiply the number of shares times the price, and we'll do the same thing for the share for the stock shares. So that'll be delta times S, and then you add them up, and you're going to get the wealth. So the wealth, these two, this is, let me write that with red. Right, this here is the number of bank shares, and this one here, this is the number of stock shares. We can write an equality sign here, and what that means, this equality sign here, this has there's a name attached to this this property here. This is called the self-financing condition. And the self-financing condition says that instead of putting k's here on the number of shares that you have, you put k minus 1. And then you keep the prices. So what it means is that by trading, when you're moving the number of shares in the bank, and you're moving the number of shares in the stock, when you're rebalancing, you're not going to create new wealth. So the wealth after trading is exactly the same as wealth before trading at time k. So the wealth before trading at time k, so I should say wealth just before trading at time k equals wealth after trading. So there's no consumption, and there's no income, there are no dividends, no consumption, there are no dividends, and no, what else? Income. One could imagine that at time k, you will also be able to receive salary, right? And then the wealth after trading might be different than the wealth before, because you would have had income. But we don't have that in our first model here. Later on, we are going to get some consumption, we are going to get some dividends in there. But for now, this is the self-financing condition. It just says that the wealth that you have after trading at time k is the same thing as the wealth you had immediately before trading at time k. You do not create extra wealth simply by rebalancing from the stock to the bond or vice versa. So that's called the self-financing condition. But and what we had in the one period model, what we had was we had the wealth. This here was our wealth. We had delta naught times S naught at time 1 plus delta times S1. This would be our put or call payoff. This would be our F of S1. And you can see here what we have used is the bottom formulation, but we could equally well have written the top formulation. We could have written ones here and ones here. That would be the same. Are we good so far? We could also have written that you have here delta naught 1 is 1 plus delta 1 is 1. Could have done that and demanded that that would be equal to f of s1. And it's custom to do such a revision. It's custom to do something like that. For example, so often we express the investment, this one here in the bank. Often we express this in terms of x. So instead of solving this equation here for delta naught and delta, we would re-express this delta here in terms of x. And let me show you how to do that. So if you're looking at the bottom formulation here, what could we have? We'll have you're looking at, so the bottom formulation was this one, so that's equal to that one. So often we can write here xk is equal to, what would it be? Well, we'll have delta k minus 1. And then instead of sk, what I'll do is go back to the definition of the bank account. Right? And so I can pull out a factor 1 plus r. Pull out a factor if I want to write here sk minus 1 is 0. I can pull out this factor 1 plus r here, because when I take the product of these two, I get exactly that one. So I'll do that, and then I'll leave the other term alone. And now I'll use the first part of here. This quantity here, this is nothing else than xk minus 1 minus delta k minus 1 sk minus 1. So I'll be able to replace, and this is where the substitution happens, right? This is the investment in the bank. I can re-express this in terms of x and delta. So I'll substitute it in here. I'll get here that this is xk minus 1 minus delta k minus 1 sk minus 1 times 1 plus r. And then the last term, delta k minus 1 and sk. And this here has one can then rearrange again. You can collect the terms that has to do with delta k minus 1 over here. So let's do that. So we can put delta k minus 1 here, then I'll have sk minus, and then it's going to be sk minus 1 times 1 plus r. And then over here, you will have xk minus 1 times 1 plus r. So that's one expression you will see in a textbook. Very often you'll see, you also see expressions of the form. You see you have xk here and you have xk minus 1 here. If I move that to the other side, I'll get xk minus 1. That one is equal to xk minus 1 times r. And then plus the stuff over here, plus delta k minus 1 sk, and then you'll have minus sk minus 1 minus sk minus 1 times r. And the reason that people write it like this is because you want to recognize that this here is the change in wealth. This here is my delta xk. And then you see here, this is the change in delta sk. You see the definitions. So you have that the changes in your wealth process is given as this formula here on the right hand side. So you can write the change in your wealth is equal to r times the wealth you had in the previous period, plus, and then you have delta k minus 1, the stock, the number of shares that you have, times the price changes, minus a discount of this part. These two here, the ones that go together and will create this delta naught to begin with. So often you'll see the wealth re-expressed like this. And we could, for example, have done that here. We could also write this, but we could also write other things. We could also write here. Also write here in this one period model. So in the one period model, we could write, we could do the same trick, right? I could write delta naught times, and then S1, I'll use the formula for it. So this will be 1 plus R times, if you want, this guy, but this is what we always put equal to 1, and then delta S1, that you want this to be f of S1. This quantity here is the one that's always set to be 1. And then you can play exactly the same game as before. You can say that instead of keeping track of the number of shares in the bank, what I want to keep track of is so 1 plus R goes outside, and so here I'll have my initial wealth, and then there'll be a change. So it'll be the number of shares times the stock price. Right, so this here is the same as saying that this thing plus delta S1 is f of S1. And then you can combine the expressions as we did before. You'll have that this is x0 times 1 plus R plus delta S1 minus S0 times, there's always this 1 plus R we have to remember out there, that this is equal to f of S1. And then instead of solving for delta naught and delta, we can solve for x naught and delta. And x0 would be the price of the derivative of the payoff at time 0. Before, what we would do is we would solve this equation here, and then we would go back, and then we will say, well, what is the price then? Well, the price is the number of shares times the prices at time 0, and then that would give us x0, but we could substitute all that in to begin with and just solve this equation here. Are there questions on this? So there are several ways to re-express these formulas, and this one here for the multi-period model, this one here seems to be the one that the textbook prefers that we use, and so I'll go along with it. Any questions up to this point? Let's try to work this out in a specific 2-period example. So let's look at a 2-period example. So let's look at it in a 2-period example. We're going to have that stock price. So it's a 2-period example. So we will have time 0, time 1, time 2, and we'll start it out. So this will go from $4. This is our stock, and then it will go up to 8 and 2, and the 8 can go up to 16. The 8 can go down to 4. The 2 can go up to 4, and the 2 can go down to 1. So we will have here that U is equal to 2, D is equal to 1, and I think he puts the interest rate to be a quarter. We also have the bank account. The bank account will go from 1 to 1.25 to 1.25 squared. This is the bank at time 0. This is the bank at time 1. This is the bank at time 2. So that's our two-period binomial model. It has a oh, sorry, yeah, d is equal to half. Thank you. He always plays with this u and d, the product being 1. And this one here is also really good because if you remember the formulas from last time, these things here decombine, so you get these p tilde is equal to q tilde is equal to half. And this is why he likes this particular configuration, u and d being half times 2 and then r being a quarter. It gives us these risk neutral probabilities we talked about last time to be equal to half. It doesn't have to be like this. You could equally well have chosen d to be 1. That was a misprint. I didn't mean to do it. But you could have had a model that d is equal to 1. And as long as 1 plus r sits in between d and u, you are free of arbitrage, and that's the only requirement. Yeah, but thank you for pointing out the typo. So how do we do it? Now we look at a put. So we have a put with strike 5, right? So the payoff, f of s1. Now it's f of s2. We're getting the payoff here at the end. Getting here the payoff at the end. So this is a put is 5 minus s2 positive part. So we need to go about trying to figure out what the price is. Well, let's look at the payoff. Let's look at the payoff. So we're redrawing the tree. We redraw the tree. So here's time 0, time 1, time 2. Now out here in the end is where the payoff is given. So this is 5 minus. So what do we have? We have 5 minus 16 positive part. 5 minus 16. This is minus 11 positive part. This is a 0. Then it is 4. Okay, so we have 5 minus 4. That's a 1. And then you have 5 minus a 1. That's a 4. Right, so that's the payoff. And now our goal is to figure out what to put here. Our goal is to figure out what to put here. And remember, when you do a multi-period setting, the way to go about solving it is to break it down into one-period models. And so how would one go about breaking it down? Well, if you start from this end out here towards the right, and then you move to the left, you'll see that this top part here, this is nothing else than just a standard one-period model. The same thing with the bottom corner here. This is a standard one-period model. So that will allow me to fill in what's here and what's here. And then we have yet another one-period model. So if we can break this into 3, we could break this into three one-period binomial models. So if you're willing to do 3 times the amount of work that we've been doing in the previous lectures, well, then we can figure out what to fill in here. Okay, so the way that we go about doing it is we start up here. So here we have had a coin flip that took us up. We've had a coin flip that will take us up here, or there will be a coin flip that goes down there. Okay, so let's try to do it. I want to have my wealth. I'm seeking, right? So we're seeking X naught, right? That's going to be my question mark. Then I'm seeking how to trade at time 0. I'm seeking how to trade in time 0 and how to trade at time 1. So we're seeking these 3 quantities. This is the number of shares at time 0, the number of shares at time 1. The number of shares at time 1 is going to depend on whether we're upstairs or downstairs. So that's what those are the 3 quantities that we're trying to determine. We're seeking these guys, and how to do it. Well, we want the replicating property is that my wealth out here at the end at time 2 is exactly equal to this payoff. So that was 5 minus S2 positive part. And so what I'll do is I'll use one of the formulas before. I'll use the formula that says that my wealth at time 2 can be written in terms of the wealth at time 1 plus this stuff over here. Right, so k is now equal to 2, so I'll get x1 times 1 plus r plus delta 1 times s2 minus s1 times 1 plus r. So I'll plug that in. This quantity here, this is the same thing as asking that x1 times 1 plus r plus delta 1 times, what was it, s2 minus s1 times 1 plus r, that this is equal to 5 minus s2 positive part. Right, so I'm working here on the end model, right? So I'm trying to go from time 2 to time 1. And as before, right, we have two possibilities here. If I'm sitting up here, there's an up possibility and a down possibility. So what I have here is really two equations. This is really two equations and two unknowns. Just as in the one period model we had last time, to replicate, it means that you satisfy this equation here in both the up and the down state when you're sitting out here in this node. Let's try to write this out. So we'll have here that x1 times 1 plus r plus, and then delta 1, this is the number of shares that I have. And now S2, there are two possibilities. Either it's going to go up or it's going to go down. Right, if it goes up, I'm going to get S1 times U minus the other thing, S1 times 1 plus R. This is going to be equal to, and so here I'll have 5 minus, and then it's S1 times U, positive part. That was when I was sitting here and wanted to go up there. Same thing for the bottom. Nothing changes in the first part. This is x1 times 1 plus r. The other one, this is delta 1. And then I'll have S2. S2 changes now because it's S1 times D. Minus S1 1 plus r. This is equal to 5 minus S1U, positive part. So now we have two equations and two unknowns, and we can go ahead and solve. So we can now solve for these. Was there a question?
Yeah, for the second equation, why is it equal to 5 minus S1U? Okay.
It is not, it's a typo. It should be D.
Thank you.
Thank you. So we solve these two equations for x1 and delta 1. We have done that a few times. I'm trusting that we can do this. If we go back to the, we can plug in exam. You can plug in calculations if we so desire. So you can solve in general using Mathematica, for example, or you can plug in the numbers and see what we get. Let me try to work it out in Mathematica. If I can get it to work. So I'm hoping we can all see Mathematica here. Let me try to see if I can get this to work. What are we trying to do? Is we're trying to solve two equations and two unknowns, and let's just see if we can get Mathematica to help us. So we're going to try to solve x1 times 1 plus r plus, now we have a delta 1 times s1 times u minus an s1 times 1 minus 1 plus r. We want this to be equal to, what did we call this payoff? I think we called it I need to call it something like, what was it, 5 5 minus S1 times U, positive part. So positive part, I think maybe I should just plug in numbers here. So R would be 1.25. U would be 2. This would be 1.25. And then in the up state, we would have a 0. And then we would also need to do something similar in the down state. So this wouldn't change. This thing here would change. Instead of U, I would have a D. And then instead of a 1 here, I'll have, instead of a 0, I'd have to have a 1. And the two things that I'm solving for is x1 and delta 1. Cross our fingers and see what we get. Here's what comes out. So I haven't plugged in what S1 is. S1 in the upstate. S1 in the upstate was, I need to tell them what it is. S1 in the upstate was 8. Put up 8 here. 8. And then we get this number. So then we copy paste that back into the spreadsheet. We open this note here. Here my x1 would be 0.4, and my delta 1 would be 0.833. I think this is the same thing as 1 over 12. Yep, that's 1 over 12. So we solved that one. We will also have to redo the same thing, but now in the downstate case. So I'm not going to rewrite all of that in one more time, but in the downstate, S1 is equal to 4. And we'll have to change the right-hand side. So this would be a 1, and this would be a 4. And then we solve again. So here we'll have x1 would be 2. And what would my delta 1 be? Delta 1 would be minus a half. Any questions on this part? Any questions out in the chat? No, so let me just reiterate. We're not putting in S0 here. What we are putting in is this. What we are putting in is this formula that we had derived. Right? We're putting in this formula here. So x2 can be written as x1 times 1.25 plus delta times this difference here. So if I plug that in to the formula, I will have these two equations ultimately. I'll have these two equations here ultimately. I'll have instead of, I wouldn't have S0 here. I would have to have X here. The goal was to replace the investment in the bank by the wealth at the time. And And so these are the two equations I was solving for the specific values, for S1 being, what was it, 8 and 2, and for D and U to be, D was a half and U was 2. Is the structure of the binomial model going to be a lattice? So if you're, it depends on what we mean by a lattice, but what's going to happen here in this particular model is that when you move along in a binomial model of this sort, whether you go up or down, or if you go down and up, this is going to become the same in this particular model, right? So the recombine here into a 4. So we can go up and then down, or down and up. This is going to recombine. And the reason that it recombines is that you go from 4 to 8 by saying 8 here, this is equal to 4 times U, right? And then how do you get to 4? Well, this will be 4 times U times D. Okay, so the other trajectory you could go on would be from 4 times D, that will give you your 2, right? And then the next one will be 4 times D times U, and that'll bring you up to U to 4 here. And whether you multiply D and U or U and D, you're going to get the same thing. So it recombines. And that's a feature of these binomial models that we're considering right now. Is what you're referencing when you say a lattice? That it has to recombine here into, so you only have 3 possible values at a time 2 instead of 4. Is that the question? Yeah, so in these models here, it recombines. These are called recombining trees. That and you can see it's much better to have this recombining property because the number of submodels that you have to consider is much smaller. Okay, so enough about that. Let's fill in the value. So let me just make sure I copy pasted this correctly from my Mathematica. Yeah, so here we have x1 is 2. This is the replicating portfolio, and this is the replicating portfolio in the top part. So now how do we fill in the question mark? Well, how do we fill in the question mark is you go back to Mathematica and you solve the last model. At this point, we have solved the top part, we solved the bottom part, there's one more that's left. And now what are the payoff values? Well, the payoff values are going to be this 0.4 and the value 2. So we have to move these two, 0.4. Was the delta for the up case negative? I don't think it was. I don't think it was. It was. It's minus. Thank you. You're good at spotting these mistakes. So what we're going to do now is, I think this is wrong, right? S1 is not equal to 4 here. S1 in the down state at time 1, S1 is not equal to 4, right? What was it? It was equal to 2. It would either be 8 or 2. So this is the correct one. This is the correct one. So it's minus 1. So what you need to do to get the last one fixed is you copy paste this thing one more time. And now your S1 is equal to 4. And you're going to be interested now in solving for x0. And then here you will have delta 0. You have S1 times 2. So that's going to be the same. This is going to be the same. But a 1 here, that's going to change now because that 1 is the value you get in the up state. And the value you get in the up state was this 0.4. So we put 0.4 here. And then here will be x0. This would be delta 0. And then you have the same values. And then instead of 4, you put the value in the down state. The value we just computed in the down state was 2. You go ahead and solve for the initial values of the wealth and the replicating portfolio. And you get something like this. So we can fill in these last values. So this is x0 and this is your initial delta minus 0.266. So let me write them in here. This is x0 was 0.96 and delta 0 was minus 2667. And there you go. We filled it all in. We know what the initial value was for replicating, and you know what the strategy is. Initially, you have to hold that many shares, and then depending on whether you go up in the tree or you go down in the tree, you will get -1/12 or -1. So this is how many dollars you need to begin to set up this replicating portfolio. You need 96 cents. So it's how you trade. So you need to start out with this minus 2.667 shares, and then you got to wait and see what happens in the first coin flip. Are you going to go up? Is this going to be heads or is it going to be tails? Well, if it's heads, then you go up here, and then you need to rebalance. You need to go from having this amount of shares to having that amount of shares. And if you go down, well, then it's going to change too. And if you go down, you're going to be selling even more because you have to decrease your position to -1. And then you're here, so now you have 40 cents, and this is exactly enough to set up a strategy that will have the payoff 0 and 1. And here you have $2, and this is exactly enough to set up a payoff that will have 1 and 4. Are there any questions on this part? Well, thank you for catching all the sign mistakes. This is what happens when you don't use slides and write this code in real time. So when you see these mistakes, please just write in the chat, and please continue to either write in the chat or just let me know about these sign mistakes. Are there any questions or comments? This is how we do it in a specific example. So the alternative is to use risk neutral probabilities. Like in the one period model, we saw last time. In one period model, we saw last time that if you wanted to price a payoff, if you wanted to get X0, then the way that you would do it is you would compute the conditional expectation. And then what you would do is you would discount the payoff. So if the payoff was a function of S1, they would have to discount it by 1 plus R, and this would give you X1. Like these were the risk neutral probabilities. So what those are those P tilde. Those are those P tilde times 1/1 plus R times F evaluated S0 times the upstate plus, and then it was 1 minus P tilde times 1/1 plus R times F of S0 times T. Right, and what is P tilde? Where P tilde is found by the requirement that the stock, look at the initial stock price, I want the expectation under those tilde probabilities of the future stock divided by the bank to be equal to S0. And as before, we just work out what it is. This is P tilde. You have the discount factor 1 plus R, and then you have S0 times U plus, and then you have your q tilde, so that's 1 minus p tilde times 1 over 1 plus r is 0 times d. This is your one equation, one unknown, and you can see S naught cancels out. It's irrelevant for p tilde, and you just solve for p tilde. One equation and one unknown, you can solve it. We can solve it. This is the same thing as saying, this here is the same thing as saying that 1 plus r equals p tilde u plus 1 minus p tilde d. And we can solve this thing here. We collect the terms that involve p tilde, put them next to each other. And we're almost there. This says that p tilde should be 1 plus r minus d divided by u minus d. Right, so we can use this formula here to calculate x0. It will not give us, it won't give us delta 0, but it will give us x0. It will give us that initial price that we have to pay to set up the replicating portfolio. It does not give us delta 0. It will only give us x0. So this is how it works in a one period model. So in a two period model, this is where the mess starts. Some more paper. In a two period model, in a two period model, so in a two period model, what would we guess here, right? So now I want to have that x2. I want to have that x2 is my f of s2. Okay, so I can discount. So I can say that this is x2 divided by 1 plus r. This is no difference here, right? I'm just dividing by a positive number, tomato, tomato. And so how do I get my x1? How did we get that value? How did we get that value over here? Well, it's not an expectation, right? Because it's random, right? It depends on whether we go up or we go down. Like x1 is not the same in this node and in this node. x1 is either 0.4 or 2. So there is a, so what we need, we somehow need to take the conditional expectation of this quantity. So this is x2 divided by 1 plus r. Right, so that's going to be, but here there is I want this thing to be equal to x1. And there's a need here to keep track of whether we've gone up or down in the tree. And so there is this conditional expectation here. And that looks funny. But what is this? What does it mean to compute a conditional expectation? And what is this f? You can see there are similar letters. This is an F with 2 lines down. This here is an E with 2 lines down. There's a tilde here. There's no tilde over here. Here we're conditioning. Here there's an F1 and an F1. This 1 here indicates that we're sitting at time 1. So this 1 here is related to the 1 over here. So this operator here is something that takes us from time 2 to time 1. Something that takes us from out here to in here. And to give you an idea about what we have been doing in previous years when I taught this class, this point, we would switch gears, and instead of working through stochastic calculus for finance 1, we would switch over and start using stochastic calculus for finance 2. And if you look there at the table of contents, there will be the first 2 chapters we'll talk about general probability theory, and then we'll talk about information and conditioning. He will talk about sigma algebras and general conditional expectations. So you can see by the time that you're doing general conditional expectations, you are down to page 75. And so page 75, this is a sizable chunk of pages, and it's like that much material. So in the previous years when I taught this class, this is what we would do. We would stop here, we will switch textbooks, and we'll spend the next couple of weeks doing general conditional expectation out of the second volume. So some students have said that we should not do that because at the end of the day, this is just the amount of knowledge that we get out from these next couple of weeks. This is not enough to justify spending so much time on it. So now I'm kind of stuck in a pickle because on one hand, I agree with the students, but on the other hand, we also need to make sense out of these operators here. Like I need to say something about it. And so that's where I am. So this year, we're going to try something different. And we're going to see how that works. But this is the first group of students that I'm trying to do something different with of all the years that I've taught this material. And I'm trying to see if I can make sense out of this expression here in a way that will not take up 2 weeks of lectures. Okay, so the way that we're going to do it, in this class here is there's no way around. We need to know what a sigma algebra is, right? So we need a sigma algebra. So if here is a sigma algebra. So sigma and then algebra. And for us, so a main example is, and the way that that's written is if, and then it's defined as a sigma, and then you write your psi in here, where psi is one of these Bernoullis. This is what we really need. So you can go up to U and D. The sigma algebra, this is the sigma algebra. I'm going to start writing sigma here instead of all the letters. This is just sigma. The sigma algebra generated by psi. Okay, so what is that? It is a sigma algebra. And here's a specific example. It's the one that's being generated by this random variable. Okay, so a sigma algebra. So this is just an example. A sigma algebra, if it satisfies a bunch of things. If satisfies that it's a sigma algebra. What does that mean? It means that if my entire omega, this is my sample space, this is where psi goes from, right? Psi is a function that goes from omega, right? And it takes two values, U and D. Right, so we will have that psi of heads would be U, and psi of tails would be D, and my omega would be heads and tails. So there are two possibilities. You can either go up or you can go down. So it's a function, the domain is omega, and the codomain, the image, this is, in this case, it consists of only U and D. So if satisfies that, in general, if F is a sigma algebra, it satisfies that omega, all of it, is in there. It satisfies that if I take a set in there, then the complement is also in there. And then the third property it satisfies is that if I take a collection of sets in there, then the union of those sets will also be in there. And that's what it means in general. Now, for our specific example, what does that notation mean? So sigma of psi means So this is the general statement. So sigma of psi means that it's a sigma algebra. So it satisfies 1, 2, and 3. And then there are two more properties. We call it A. It's the smallest. So what should we have? You have those sets of omegas. Those sets of omegas for which psi of omega is less than a constant, say x. This is a set inside the sigma algebra for any point x in R. And then B, it's the smallest sigma algebra satisfying A. Wow, so this is a long recipe, huh? This object, these random variables that we're talking about, the Bernoullis, you take the values u and d. Okay, so we will have a need to create this object here. So psi, sigma of psi. So that's the smallest sigma algebra. It's the smallest sigma algebra such that, well, to be a sigma algebra, you need these properties here. And then it's the smallest one that has this additional property that whenever I look at these level sets for psi, those level sets the inside the sigma algebra. So this can be a lot to process. This is why it has typically something we spent quite some time on, but we try to give you an idea about what this thing here looks like in our example. Right, so sigma of psi, right, it's going to contain everything in this example here. It's going to contain everything in the complement. So everything and the empty set are going to be in there. And what else is going to be in there? Well, those sets here. So let's try to have a look at what these sets look like. Like we could take the example that we had before. We could have u here. U here could be 2, right? And d here could be a half. So I'm interested in what kind of omegas can I see over here. So if I look at the set of omegas for which psi of omega is less than, this has to work for all x. So let's try to do it for less than 10. What omegas inside my sample space consists of h and t's? What kind of omegas would give me a psi that is less than or equal to 10? Well, when is psi less than or equal to 10? Well, it's always less than or equal to 10. Because it's the max value it takes is 2, right? So this here is equal to everything. So where we start getting some action, is when you get down to around 2. So if I take 2, what would I get? This will still be omega. This is still everything. Okay, so I need to go below 2. So let me put in 1. Now, what omegas can I plug into psi to get a value which is less than or equal to 1? Well, now I cannot do the head one. I can only do the tail one. So this one here comes out to be t. And then I could continue. Just when do I get something next time? A half. Well, a half is still going to do it. This is still going to work with a t. So I go less than a t, less than a half. So if I put in, say, a quarter, well, now it's going to become empty. There is no right. If I'm asking what omegas will give me a value that is less than that is less than a quarter, it's not possible, right, because the smallest value I'm getting is a half. So this is an empty set. So what I need to do is to be a sigma algebra, right, I need to be stable on the complements. So I have my omega, complement is in there, then I have a t. I need the complement in there. The complement of t is going to be h. And then I need to make sure that I'm also stable on the unions. So if I take the union of these two, I'm going to get omega. I take the union of these two, I get t. Take the union of these two, I'm going to get omega. This looks good. This is the smallest sigma algebra that has this property. The property number A. Property number A has its own label. This thing here is called. This one here is what that means is that psi is sigma of psi measurable. So for most of you, this is probably the first time that you'll see a sigma algebra fleshed out this way. So I'm happy to answer any questions that you may have about this. So let's try to do another example. This here was like the 1-period binomial model. Let's try to do the 2-period binomial model. So now the next example is we will have psi 1 and psi 2. Psi 1 and psi 2. And the IID, so you go up to U and down to D. So in this case, my sample space. Now my omega, I need more elements in here. I would have to have heads, 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 tails, tails, heads, and tails, tails. And then I can look at the same question. I'm interested in what is the smallest sigma algebra that makes psi 1 measurable. And we can write that out again. So I need to go through all these sets here. Let's just keep U and D to be 2.5. What would we get this time? If I'm looking at a set like this one, this is still going to be omega. But what about if I look at a set like this one, when psi 1 is less than 1? Right, so I'm still going to have omega in here, and the empty set, you will still be there. But what about a set like this one here? So if I look at those omegas, such that psi of 1 of that omega is less than or equal to 1. What do the omegas look like? Well, I have 4 to choose from. Right, so what kind of an omega would put me to be less than 1? Well, that means that the first coin flip would have to be tails. Okay, so I look over here. First coin flip has to be tails. This is TH and TT. And then again, I could move down further, and I would see that I get the empty set when I'm pushing it below half. So I need to put this one up there. So that has to go in there. TH, TT, and then its complement. The complement is this one. H, 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 T. And let's just check that this is all we need. So are we stable on the complements? Yeah, this is good. Are we stable on the unions? Well, if I take the union with these two, I get omega. Union with these two, I get that set. Union of these two, I get omega. Right? So that's the smallest sigma algebra that makes psi 1 measurable. So what about the next one? I could also look at the smallest sigma algebra that makes both psi1 and psi2 measurable. Okay, so what kind of sets am I interested in looking at now? Well, this is the smallest sigma algebra that makes both psi1 and psi2 measurable. So maybe we should have a look at, so we have an idea about what psi1 is. Okay, so let's do psi2. What is the sigma algebra here? It's going to be very similar. This is just going to be the second entry that's going to be the determining factor. If I look at a set like this one, those omegas for which psi2 of omega is less than 1, what would that be? Well, psi2 only cares about the second component, right? So what would I find in here would be something like it could be heads on the first. It doesn't matter. This one here will only see the second one. So if I have a tail, then it's going to work. Or if I have the first one could be tail, and then the second one could be tail. So that will be in there. The second entry is what determines the psi2 value. And I want to get something that is less than 1. So if the second entry here would be heads, I would be equal to 2. If the second one here is tails, if you have psi2 of ht, this is equal to d. Psi2 of tt is equal to d. Psi2 of, say, heads, it only sees the second one. This one here is equal to 2. Psi2 of tails, heads, this is equal to 2. And d we have put to be equal to 1/2 in our example. All right, so if I want this thing to be less than or equal to 1, I can get ht and tt. All right, so that would have to go in there. So my sigma of psi2 would be omega, empty set, this guy. And then the complement would be over here. This would be h, t, h. So now what I need to do is I need to make this, I need to be able to, so inside here, I'm going to find both these sets. So what I need to do is, so sigma of psi1, psi2 is going to be equal to omega, the empty set, and then both of these. th, tt, h, ht, ht, tt, and then this one. And then I need to check that it is stable on the complements, and it's stable on the unions, and so on. And this is where we start seeing a difference, right? If I take the union of these two, I'll get HHTT. Right? If I take the union here of these two sets, the union has to be in there. So the union is HHTT, but that's nowhere to be found. So that union has to go in there. So we need we need to add the union of H, H, T, T. So that had to be there. What else could we put in there? We will have to add, this one is good. We have to add the union of these two. Again, the TTs, the comment. So this is the point here. I take the union of these two, so I'm going to get HHHT, and then this one is already there, and then I'm going to get TT. I'll do the same thing with the next one, right? So take a union of these two. This will be THTT, and then what do we have in here? This is an HT, and so that was these two, and the same thing with these two here. This will be THTT, and then the union what you have over here. This will also give me an HH. And then the last one would be HHHT, and then union with this one, we'll get a TH. Oh gosh, but then I also need to be stable on the complements. So then what will I get here? If I am to be stable on the complements, if I take the complement of this one, the one that is missing is TH. And the one that is missing in the next one, this is, I need to be stable on the complements. Complement of this one is TH. The complement of this one, this is going to be HT. And lastly, this one, the complement here is going to be HT. I feel like I messed something up. HH. The complement of this one here is going to be HT. We already have. No, the complement of this one is going to be TT. There you go. Okay, so this should give me, as soon as I get these single ones in here, then I have to have all the sets, right? Because it has to be stable under all kind of unions. So as soon as I have the 4 singletons, then I'm going to be stable on all unions. This here is going to be equal to this set of all omegas subsets. And that's because you have these 4 coming out. So you can see these sigma algebras, they're different. There's a lot more inside the sigma algebra generated by psi 1 and psi 2 than there is inside psi 2 sigma algebra and inside psi 1 sigma algebra. And all 3 of them are different. So what we're going to do is, for us, what we are interested in. So our model uses sigma algebra, psi 1, psi 2, up to psi n. It uses this guy here, and we're going to call him for Fn. This is the smallest. This is the smallest sigma algebra. Which makes psi k measurable. So that means that these sets, those omegas, such that psi k of omega is less than x, this belongs to for any x in R and for any k between 1 and n. This here, this is called the filtration. So that's also a new word. It uses the sigma algebra being generated by the n first conflicts. So that's what Fn is. It's a sigma algebra, and it has this property that it makes all the first n conflicts measurable with respect to it. So in our case, we have the two-period model. Two-period model. So in a two-period model, we will use F0, which is the first one. So that's going to be a very easy one. That's going to be just the one that has the empty set and omega. Then we'll use F1. This is going to be the one that makes psi1 measurable. So that's the one from above. And then we'll use F2. That's going to be the one that makes psi1 and psi2 measurable. Right? And this is also equal to all subsets. So you go from one extreme where you just have the smallest one in the world, like this is a sigma algebra, right? It's stable on the complements and it's stable on the unions. So that's the smallest sigma algebra, and this one here is the biggest one, and then there's one in the middle. And what we note is that F0 is inside F1, which is inside F2, and that's a property of a filtration. The filtration has this growing property. You don't forget. Like F2 is to model the information that we have at time 2. F1 is to model the information you have at time 1, and so on. And so what this means is that you don't forget, but learn new information over time. So F2 is information you have at time 2, F1 is what you have at time 1, F0 is what you begin with, and here you begin with no information. And then over time you learn more and more and more, and this is captured by this inclusion that we're seeing here, that F2 contains more information than F1 and so on. The same thing is true in general. This sigma algebra, what it means is that you have seen the first n conflicts, right? And if you've seen n conflicts, you've seen more than just the first conflict and the first and second conflict and so on. So these filtrations, they are increasing, in the index that we have down below. Okay, so this is a big mouthful. Are there any questions or comments on all these slides that I've been writing up here?
I have a question. Are these topics, I guess, in a algebra course or college algebra course? Is there something that if we didn't take a college level algebra course that we could look up, or what topics to get more familiar with what you're speaking about here?
Yep. So I would strongly suggest that you get a hands on our books here. Right. So this stuff is in here. You flip over to what he's talking about in these sections. You'll find the stuff in here. Now he's getting into conditional expectations, and you can see there's an n sitting here. This stuff is in here, and there's not so much in here, but there's a lot more in his second volume. And you're going to need this book anyway for the next course in 622 and 623. If you get down to sigma algebras on page 49, you can start seeing he has stuff listed here. This is a 3-period model. Like every time you have another period, you attach another letter to it, and you start seeing the sigma algebra that comes out. Like the ones that have been listed, they look a lot like this one, right? you're taking up sets, then you start looking at complements, and then you need to take unions. And here we have the F0, that was the one I also had listed, right? And F3, this was the set of all subsets of omegas, that was our F2. So these things, they are already in our textbook. So I would not go out and start chasing, I would not go out and start chasing a different source of reading material. I would much rather just use the ones that we already have. And this is going to be plenty. The course where you will, if you have taken courses, the place to look, the search that you want to be doing is mesh and integration theory. If you want to go out and find another source, but in really like Shreve 2, and this is going to be used for 622 and 623 is a good source. We need to know what a sigma algebra is, and in particular, when we're talking about a system of them, we index this system by n, and n for us is time. And the reason that we are keen on looking at a system of sigma algebras is because of this property that you have inclusion. So over time you learn. How do you model learning over time? Well, the way that we're going to do it is by including more and more sets in the sigma algebra that we're keeping track of as time passes. That's our model for information. This is our model for learning. And the interpretation is that if you're sitting at time n, you have observed the first n coin flips, right? And now you're going to make decisions going forward. And of course, you don't know what the next coin flip number n+1 is going to be, but you do know what the previous n coin flips were. So that's the next thing that I want to talk about, is how does one work with this object? Actually, the thing that is to come, and we're running a little bit out of time, but let me just mention it. Like we need to make sense of. So for a random variable, so this again is a function that goes from omega into R. Like for a random variable x, we need to define the conditional expectation of x given a sigma algebra F. What is this equal to? What we're interested in, so for us, what we're going to be interested in is a conditional expectation of, say, F of like in the two-period model. Like what we were interested in the two-period model was to say I had a put, and the put was 5 minus S2 positive part. We really wanted to compute this condition on knowing the first coin flip. What is this equal to? Well, let's give it a go. Let's just try it out. So let's just do a heuristic, but this is actually correct. It can sound daunting to look at it, but the way you operate with these, correct, I cannot spell correct. Correct. So it's a heuristic but correct calculation. The way you operate with them is not super surprising. Like, what is this thing here equal to? Well, the way you go about doing it is you're going to relate like S2 and psi1. Like this is the first coin flip. This thing here involves the second coin flip. So what you do is you insert what this one here is. So this here is going to be this is going to be S1 times psi2. That's our model. This thing here, this is equal to S2. Because we are in the binomial model. And then we condition on knowing psi1. So we're conditioning here, and we're trying to figure out like this conditional expectation here, what is that equal to? How? So before I write down the formal definition for it, let's just try to do a calculation, like what would one expect here? Well, keep in mind, S1, that one only involves the first coin flip. The stock price at time 1 is given in terms of the first coin flip, right? So you have just a calculation over here on the side, right? You have your S1, this is just equal to S0 times the first coin flip. Right? And now you're conditioning on knowing the first coin flip. Okay, so then you have psi2. Psi2 and psi1, they were independent. Right? This symbol here means that psi1 and psi2, they are independent. So psi1 and psi2 are independent. So this is what you know, and so you know S1 and psi2 is independent. Okay, so what you do is you simply just, what you know, you freeze. So you write this here as 5 minus, and then S1, you know what S1 is, so you can just leave him be. Then you have psi2. Psi2 and psi1, they're independent, so you just take an average. So in psi2 can be U. Okay, that happens with some probability, and you need a 1 over 1 plus R here. You always need to discount 1 over 1 plus R, and then a P tilde. And again, there's also a chance that it can be D, so we need to add that on. So this is 1 over 1 plus R, 5 minus, and then S1. S1 is known because you're conditioning on knowing the first coin flip, and then you get a D here in positive half. So you can see now what this conditional expectation here is. This is a function of S1. This random quantity up here is a function of S1. Right? But S1 is, of course, nothing else than a function of psi1. Right, so conditional expectations. So the conditional expectation of 1 over 1 plus R, conditional expectation of 5 minus the stock price is 2 given psi1. This is a function, so let me call it something, f of psi1, where say f of x, this function here is this long mess. This is p tilde divided by 1 plus r, 5 minus, and then you have your x. Your x, this was your x here, this is going to be a psi1. So psi1 times s, that goes in there, and then you have a u. Positive part plus 1 minus p tilde, 1 over 1 plus r, 5 minus, and then S1. S1 was S0, x, d, positive part. Right, so it's this sort of definition that we're looking for, like these conditional expectations are functions of those random variables that we're conditioning on. That's how it's going to be ultimately defined. This thing here, if I wrote this as a conditional expectation of psi1, this is equal to a function of psi1 for some function which goes from R to R. But which one? But which one? And so I can see we're more than halfway through. This is what is coming next time. So today I introduced sigma algebras and I talked about filtrations. What is coming next time is like, what is the actual definition of this conditional expectation? Well, in this particular case, it's going to be a function, and we even derived what the function is in this particular case. Like there's no randomness in the bottom line here. It's just x. X sits here and it sits here. Everything else is a constant. This is a non-random object. And that conditional expectation is going to be that function evaluated at that random variable. So this is going to be a random variable. This thing down here is not a random variable. But of course, there are lots of such functions like cosine, sine. Why is this one here the correct function to write there? Well, which one is it? So this requires the definition of what we mean by conditional expectation. But I wanted to do this heuristic calculation today, and then hopefully you guys can think a little bit about it. And then next Tuesday, I will continue with this sort of material here. Are there any questions before we take a short break? All right, so after the break, I'm going to shift gears and we're going to move away from all this math here. And we'll start doing a bit of swaps. So let's take a 10-12 minute break and then switch over to the other Zoom link, and then I'll see you in a little bit.